In this video, we'll be discussing the conservation of linear momentum for a control volume, and we'll be applying it to real-world situations. So similar to conservation of mass, we're going to use the Reynolds transport theorem. So looking back at learning objective 26, we had the Reynolds transport theorem for a steady and uniform flow at inlets and exits is simplified down to this equation, which on the left side is the rate of change of our extensive property in our system. And on the right side, it's the net flow rate of the extensive property exiting across the control surface, so going across the boundaries of our control volume, where capital B is going to be our extensive property, whichever we choose it to be, and lowercase b will be our specific of that property, so divided by the mass. Also, before we can get into this, though, we need to take a step back and look at Newton's second law. So most people, when they think of Newton's second law, think of F equals ma. Think of the summation of the forces equal to mass times acceleration. This is actually not all of Newton's second law. Newton's second law really says that the summation of the forces is equal to the change over time of the momentum. So why do people make this mistake? Well, let's look at what the product rule would be for this equation. So if we take the product rule, we would get that mass times the change in velocity over time plus velocity times the change in mass over time. Well, if we're looking at a solid object like a baseball, a football, or just some block, the mass of that object is not really going to change over time. So the second part of the equation becomes zero because the mass doesn't change. So for solid objects, you just look at the first term. And so the change in velocity over time is acceleration. So if you're dealing with a solid object, then yes, F equals ma is enough. However, since this is a course that involves fluid dynamics, we're going to have to look at the entire change in momentum, not just the change in velocity. Okay. So the sum of the summation of the forces equal to change in momentum. That's equation 3.3 in your text. So we're going to apply this equation with the Reynolds transport theorem. Alright, so looking back, Reynolds transport theorem for steady uniform flow at inlets and exits, we're going to make momentum our extensive property, because we're trying to look at, see if we can conserve it, which would mean then our specific property would be momentum divided by mass. So if momentum is mass times velocity, then our specific property is just velocity. Okay, so let's plug that into our Reynolds transport theorem. As you can see, we have it there. Well, like we just said, the change in momentum over time is the sum of the forces. So we can rewrite this as the sum of the forces is equal to the summation at the exit of the mass flow rate times the velocity minus the summation at the inlet of the mass flow rate times the velocity. This is equation 3.27. It's also located on your reference data card. Now, some notes for using this equation. This is an equation that's going to be pretty tricky for a lot of students. This, along with hydrostatic forces on a submerged plane, are probably the two biggest trouble areas for cadets taking this course. Some quick notes. If atmospheric pressure is used, we just use gauge pressure. Now the reason this is if atmospheric pressure is outside, so the way you would know that is that they would say we're looking at a pipe, the pipe opens out to atmospheric pressure, or the pipe starts at atmospheric pressure. If there's atmospheric pressure involved in how you're balancing this equation somewhere, you have to think that atmospheric pressure is then acting on all sides of this control volume. So the atmospheric pressure really cancels it out. So if the atmosphere cancels out, then we just can look at the gauge pressure. This is one of the few times in this course when we're going to recommend you use gauge pressure and not absolute. Okay, so if atmospheric pressure is outside, we're just going to simplify things and use gauge pressure. And you're going to see it's going to make a lot of things cancel out, make things a little easier. Another key thing is that pressure always acts normal to a fluid. So it's normal to a fluid, so it doesn't really matter what direction the flow is going. It matters more what the pipe orientation is. And you're going to see this when we do the example problem, how the pipe orientation is more important than the flow direction of where the liquid's going. Okay? And the third keynote we're going to say is that in this class, we're much more dynamic than, say, MC300. So the sum of the forces is not always zero. You may have force left over. Okay, so don't just make the assumption that the forces have to equal. Now, these forces have to balance with the momentum, but the forces do not have to equal 0 because you could have the momentum left over. All right, so we're not saying the left side does not have to equal 0. It has to equal the change in momentum. Okay, very key. All right, so let's look at an example problem. Now, example 3.4 in your text. What we know is that water flows through a reducing pipe exiting at atmosphere. So that's key. It's going to the atmosphere. They want us to find the reaction force of the pipe to water and the force of the water on the pipe. Okay. So they're asking for two things, but let's think about this. The reaction force of pipe to water, so that's as the water hits the pipe has to hold it in place. So that's the reaction force. And the force of the water in the pipe. Well, if you can find the reaction force, right, if the pipe, now in this case, if the pipe is holding it steady, then all of these forces will be equal and opposite to that reaction force. Okay. Now, we're going to show you in the equation. You can't jump to the assumption that forces are equal to 0 on the left side. But we're going to show you that if you were to subtract the momentum, then yes. And if you just have that change in momentum, then yes, you could say that everything's on the left side is going to be 0. Just, if that's a little confusing, just stick with us and you're going to see how this is going to play out. Okay. So when we do diagram and data for linear momentum, we always recommend you do a force and momentum diagram. The reason you do a force momentum diagram because the left side of the conservation linear momentum equation is forces, the right side is momentum. If you draw your force momentum diagram correctly, then you just have to copy the items on the force diagram down to the left side of your equation, the things on the momentum diagram to your right side of your equation, and you will keep them straight. If you put them on one diagram, chances are you're going to put them on the wrong side in your equation. Okay, so when you do these problems, you always should start with a force diagram and a momentum diagram. Okay, so force is acting on here. We're going to have the pressure of the fluid. Okay. So we can see how the pipe is drawn. You can see that the pressure force is always going to be normal to that cross-sectional area. So in 1, the cross-sectional area, we can see it's going, that pressure force is going to go completely horizontal in the x direction. However, at point 2, because the cross-section opens up at an angle, that pressure force is coming back, because it's normal, so it's got to come into our system, but it's coming back at an angle as well. Okay, so it's the direction, excuse me, the angle of the pressure force is going to be dependent on how that cross-sectional area of the inlet or exit is. Okay, it's always going to be normal to it. The direction of it's always into your system. You should never have pressure forces going out of the system. They always come into the system. Okay, so the arrows always need to point into the system. Okay. Another force we have is all the water inside the pipe. It's going to have some weight. So we have a weight force of all the water in the pipe. So we have water coming into the pipe, but if you think about it, if you were just shoot water into a nozzle, like say you take a solo cup, cut the bottom of it out, and then shoot a hose into it. As it hits the side of the cup, it's going to try and push the cup away, right? It's not just all funnel through all by itself. So something has to hold that cup in place. So what's holding this pipe in place, as the pipe is being reduced, is going to be a reaction force. Now, the direction you draw your reaction force is not important. The important thing is you are consistent between how you draw it on the diagram and how you put it in an equation. Okay? And we'll see that in how the answer comes out. So you just have to guess a direction. It doesn't matter if you guess wrong or right. You'll find out which direction it's actually going when we solve the problem. So that's the force side of the equation. On the right side, we got momentum. Now, on the left side, we said pressure always goes normal. The momentum goes with the direction of the flow. All right. So in this case, momentum 1, it's also going to be normal to your cross-sectional area, but it's with the direction of the flow. So it's going normal and in to the pipe, and at point 2, it's coming normal and out. They also give us for this problem the numbers for the mass flow rates, some velocities, those diameters of these pipe. We're going to assume it's a pipe, so it's just a circle to determine the area. They give us the pressures and the weight. The reason, like we said, we talked about why it's beneficial to use gauge pressure. So you see then, we said it exiting to atmosphere, which means we can use gauge pressure. We'll look at pressure 2. It's going to give us 0. It's going to reduce a lot of our equations, make things really easy for us. Okay. So let's look at those assumptions. Always got to state our assumptions. Now, obviously, we're probably going to want to use the conservation of momentum at control volume that you have on your reference data card. In order to do that, you can see how it's labeled on your reference data card. That's for a steady uniform flow. So we're going to assume steady uniform flow. We're also going to assume atmospheric pressure all around because they already told us that's exiting, so then it must be everywhere. And so we can use gauge pressure at our inlet and exit. So analysis, we already said we're going to use our conservation of linear momentum. But we're going to break it up into the coordinate axis. So we're going to solve it in the x direction and the z direction. Okay. So let's start with the x direction. So just looking at the x direction, we look at what forces we have. So on the force diagram, we have the pressure force at point 1. Okay. We have a reaction force in the x direction. Weight is only in the y direction, so we don't have that. And we have a component of the pressure force at point 2. Now we don't have all of it because it's coming at an angle, so we only want the x component. So we know it's a 50-degree angle, and if we do our trigonometry, we can find that in order to get the x component, we're going to have to multiply it by cosine of 50 degrees. Okay? So those are all of our forces in the x direction. Now we have to balance that with the momentum. So our momentum at the exit, we've got, it's 1 in the 1 exit. We have 1 exit is 0.2. It's also coming at an exit and we at an angle, and we only want the x component. So we're going to multiply it by cosine of 50 as well, and then we subtract the inlet momentum. Now again, like we said, benefits of using gauge pressure. So we said gauge pressure at point 2 is going to be 0 because it's opening to the atmosphere. So if it's opening to the atmosphere, then the pressure there has to be atmospheric pressure. So we're going to have gauge pressure 0. Well, if pressure 2 is 0, then we can just cancel out that term. Another way to simplify this on the right side is that we've seen that by the data they gave us, the mass flow rate at 1 and 2 are equal. So we're just going to pull the mass flow rate out and put the change in velocity in there. Okay. Now we're trying to solve for that reaction force of the pipe on the water, so we put it in terms of the reaction force. And if you put your numbers in and do the conversions correctly, you should get a negative 50 pounds force. Now it's negative. If it's negative, that means the direction we guessed was not the right direction. So we guessed that the reaction force would go to the right. If it's negative, that means it's actually going to the left. So we say the answer would be that's 554 pounds force acting to the left on the water. If there's 54 pounds force acting to the left on the water and the pipe isn't moving, then that means there's 54 pounds of force acting to the right of the water onto the pipe. Okay. So that is all the forces to include that force that include how the momentum reacts to it. That's what the water is pushing, is being pushed onto this pipe, and the reaction force has to balance it out to keep it from moving. Okay. The way we talk about it is it all depends on what your system is. Okay. The way we normally deal with fluids is we're looking at the fluid, in this case of water. So everything is related to water. Okay. And in terms of water, we have the force of the water, the reaction force on the water, and the pressure force in the water. If they ask you in terms of the pipe, then you have to look at the forces acting on the pipe. But normally, the way we do conservation of linear momentum, we're looking at the forces on the fluid. So that was the x direction. Let's look at the z direction. So we still have a conservation of linear momentum equation. So force in the z direction, we've got that reaction force in the z direction, we've got weight, and we've also got that component of pressure force at point 2 going in the z direction. And we got and you can see that all of the momentum at point 1 is going horizontally, going in the x direction, so there's no momentum in the z direction, so it's only momentum at point 2 in the z direction. That's a component of it of times sine 50. Well, again, a pressure at point 2 is 0 gauge, so we can just get rid of that term. We rewrite it in terms of the reaction force in the z direction. We plug in the numbers of, we had the weight of 15 pounds force, we plug in our mass flow rate, center velocity, and what you get is 52 pounds force. Now it's positive, so that means we guessed correctly this time. So it should be 52 pounds force acting upward onto the water. So like we said, these are all forces acting on the water. We have pressure acting on the water, you have weight acting on the water, and this is the force of the pipe acting onto the water.